In this video, we're going to discuss how to graph transformations of basic log functions, and we're also going to discuss how to find the domain of a log function. I have here an example of a basic log function. We graphed this in a previous video, and the way we graphed log base 2 of x was by thinking about it as the inverse of the function y equals 2 to the x. So we had a table of values for 2 to the x, and since log base 2 of x is the inverse function of 2 to the x, that means we took each point and switched the x and the y coordinate, and that gave us our graph. We saw that it has an x-intercept at 1, 0, and it has a vertical asymptote of x equals 0 because it approaches the y-axis without touching it, since we have only positive x values for a basic log function. That's going to be super important to keep in mind as we work with log functions, that if it's just log base something of x, we only allow positive x values, and that's because the exponential function only had positive y values, and we've switched the columns now. So we're going to use this basic graph of log base 2 of x, and we're going to graph some transformations of that function. And the transformations are going to work the same way that they did for every other function. So for example, in this first function here, we see subtraction. Subtraction means we're doing a shift of some kind. And then the question always becomes, is the shift horizontal or vertical? It's going to be horizontal if it's inside with x, like inside the original function. And if it's not, then it's going to be a vertical change. So here we have, it's basically almost the same as our original function, but the difference is x has been replaced with x minus 1. The parentheses there are showing us that the x minus 1, that entire expression is now the input for this log function. So instead of an input of x, now we have an input of x minus 1. And we've seen before that that means the graph is going to shift to the right 1 unit. So if we have a table of values of points for the original function, then we can shift to the right one pretty easily. So if we're at 2, now we're going to move 1 unit to the right and be at 3. If we're at an x value of 1 and we move to the right, we'll be at 2. And if we were at 1/2 and we move to the right 1 unit, we're going to be at 1.5. We don't have anything happening outside the function. We just have the one transformation. So vertically, nothing's changing, which means the y values are just going to be the same. Now we had a vertical asymptote here. That's going to move with the function when we move it horizontally. So this vertical line is going to move to the right 1 unit as well. And the asymptote is now going to be the line x equals 1. And so then we can plot those points that we just got. So 1.5, -1, 2, 0, and 3, 1. And since we know what the shape looked like of the original function, we know what the shape looks like for this one. It's the same shape, just it's been picked up and shifted to the right. It's still going to approach the asymptote as we move to the left, but again the asymptote is different because the whole graph shifts. Okay, and this next one, it looks similar, but there's no parentheses this time. That's important to notice because the parentheses were showing us that the -1 was part of the input. This means the +3 is not part of the input. So we're taking log base 2 of whatever the x value is, and then after we get that value, we're adding 3. So the input is still just x. Nothing has changed horizontally. This plus 3 is outside the function. Some books will write it like this just to kind of make it a little bit more obvious that it's outside the function. But some books will write it like this, and so it's up to you to notice whether there's parentheses or not. In either case, this is going to be shifting up 3 since it's outside, not with x this time. It's not in parentheses with the x. It's not horizontal, it's vertical. So since the input is still just x, nothing's changing in the x column, no horizontal change, so we can just copy those values down. And then we're going to move these points up 3. So you can do that visually, or you can just add 3 to each of those y values there. So we have 1/2, 2, 1, 3, and 2, 4. The vertical asymptote is what it is because of the inputs, right? The reason we have this asymptote is because on the original log function, like just a basic log function, there are only positive x values. Since nothing changed with the input here, the input is still x, the asymptote will be the same because we still only have positive x values. All we've done is just picked up the curve and moved it up. Okay, here we have a vertical change again because the input is the same. It's just x like it was for the original. So once again, we have no horizontal change here. So our x column's the same, and we still have the same vertical asymptote because we're only going to have positive x values. But now we have a change in the y direction. This is like -1 times the original function. So that's going to do a vertical reflection. Because we're multiplying the function by -1. So all we got to do is take the old y values and multiply them by -1, and that will give us the new y values. So -1 becomes +1, 0 stays the same, and then 1 times -1 for that. So the point here that was at 1/2 -1 now gets reflected up, and it's above the x-axis here. And the point that was above the x-axis is reflected down below. The point that was on the x-axis is going to stay put. And all the other points get reflected as well. So you can just kind of visually see, since it was approaching the asymptote heading down, now it's going to approach the asymptote heading up. All right, we have another reflection. We have something being multiplied by -1, but this time it's x that's being multiplied by -1. We have nothing on the outside, so no vertical change. This time we have a horizontal reflection. So it's going to get reflected over the y-axis, and the y-axis is the asymptote. So the asymptote is going to stay, but the curve, instead of being to the right of the asymptote, is now going to be over here to the left. It just gets reflected over. And you can plot some points by just multiplying x by the x values by -1. So you have -1/2, -1, -2 for those same y values that we had before. and all the other points get reflected as well. So the whole shape just gets reflected over to the left side. Let's talk about how to find the domain of a log function. And there's two ways to find the domain of any function. You can use the graph or you can use the equation. If we go back to our very first basic log function here, we know that this domain was only positive values, and again that was because the range of the exponential was only positive values. So if it's just log base something of x, then you'll only have positive inputs that are allowed. Once that input changes, once there's been a horizontal change, once x has been replaced with some other expression, still involving x, but not just x, then the domain can change. So let's see what happens here. Now, instead of x, we have x minus 1. So it's still the case that we only want positive inputs, right? Just like here, we wanted positive inputs only. But now x is not the input. X minus 1 is the input. So since we want x minus 1 to be positive, we could set up this inequality and solve it for x, if you like. And we would find out that x has to be greater than 1 for this function. And we can see that from the graph as well. So you can use the graph instead of setting up the inequality. Oh, I graphed this and everything was to the right of that asymptote x equals 1. So that's another way to figure out that the domain is all numbers greater than 1. With this function, we did not have a horizontal change. The input is still x. Remember, the plus 3 is like done afterwards. So since the input is still just x, we still just want x to be greater than 0, and we can see that on the graph. It's approaching the line x equals 0. So the domain here is still just all positive numbers like it was for our original log function. Similarly here, the input is still just x, so the domain is going to be the same as it was for the basic log function. The graph is still entirely to the right of that asymptote x equals 0. With this one, however, we can kind of see from the graph the domain has changed. Now all the x values are negative. How would we get that if we wanted to use the equation instead? Well, we could still say I want my inputs to be positive. And to solve this for x, I need to multiply both sides by negative 1. And if I multiply both sides by negative 1, I need to change the sign. I need to change the direction of the sign, because if I'm multiplying by a negative or dividing by a negative, you can think about it as dividing by negative 1. That still works. Either way, you get just x. But if you multiply or divide by negative 1, then the sign reverses, and now we can see our domain is all negative real numbers. Now sometimes the input is a little more involved, like this here. So we're not going to graph functions like this, but here the input on the log is a rational function. So it's still the case that we want the input to be positive, just like it was here, right? We set the input greater than 0. Here we set the input greater than 0 and solved that inequality. And so since we don't know what the graph of this looks like, that's going to be our best way to go here, is to just take the input and set it greater than 0. And we've discussed how to solve inequalities like this previously. The left side is a rational expression that can only change sign where the denominator is 0 or where the numerator is 0. And so the denominator would be 0 at -3, the numerator would be 0 at 1. And so we can test a number in each of these three intervals and see where this statement is true. So I'm going to test -4 for the first interval, and I get a negative over a negative, which is positive. So we have solutions in that interval. -3 itself is not valid because we can't have a denominator of 0 in that rational expression. So I'm going to put an open circle there to remind us that -3 is not included. But we tested a number to the left of that and got a true statement. For the middle, I'm going to use 0. That's a pretty easy number to use. We're going to have -1/3 here, which is not greater than 0. So if we plug in 0, we get a false statement here, so no solutions in the middle there. The number 1 is going to give us a false statement as well, because we'll get 0 on the left. We'll have 0 over 4, which is 0. But this is a strict inequality. Right? 0 is not greater than 0. So 1's not going to be included. But let's test something to the right of that. And we get a positive number there, which is what we want for the inputs of this log function. We want positive numbers. So the domain of this log function is the set of numbers that are less than -3 or greater than 1.